All right, pod 12. It looks pretty straightforward. However, most of you guys saw it was pretty tricky. The first thing you want to do before you do anything with the synthesis problem is identify whether or not carbons were gained or lost. So in this case, we clearly gained a methyl group. What are two different ways we can gain carbons in synthesis problems? Alkylations of terminal alkynes, or a Grignard reaction with an aldehyde, a ketone, or an ester. Which one do you think is more likely, the Grignard reaction or the alkylation of a terminal alkyne? Grignard. In this case, you can tell too, because if we look at this carbon, there's no way for that carbon to have resulted from a terminal alkyne, or at least no way I can think of. So we're probably doing some sort of Grignard reaction, so let's just make a note. Grignard plus ketone, aldehyde, or ester. One of these we can immediately throw out though, the ketone, the aldehyde, or the ester. Which one do you think is least probable? Ester. Why is the ester probably not a likely candidate? If we remember, if we go back to our notes, let's go back really quick to Grignard reactions. We said if we have an ester like this example, and we added methyl magnesium bromide, that the Grignard can add in once, it can kick off an alkoxide, and then the Grignard can add in again. So in this case, the fewest number of carbons you can add is 2. You'd add in your Grignard group twice. So on the pod, we can immediately go back and we can say, all right, that ester is probably not a likely candidate. So let's just cross that out. And if you look at ketone versus aldehyde, which one do you think is most likely? Probably the ketone, right? If we look at the aldehyde, I don't really see any position where we could install an aldehyde on the ring without having a prior carbon already installed. So we could cross out aldehyde and we could say, all right, this is likely a reaction between a Grignard and ketone. It's really important at the start of a synthesis to just look at simple elementary things like did you gain carbons, did you lose carbons, and then just break it apart into really simple steps, kind of like we did here. All right, now let's work backwards. What's the only way we know of making alkanes? What was that? Hydrogen gas. What catalyst do we like to use? Platinum or palladium, either one is fine. And what would our intermediate be before the alkane? An alkene or an alkyne? Do you think it's going to be an alkyne though? No, if it were an alkyne, that would be a really strained alkyne. So in this case, the most likely route would be to have some sort of alkene intermediate. Okay, so we're getting there. Oftentimes, if you're kind of stuck going backwards, you can go forwards a little bit too. So let's look at our cyclopentane. It's completely unfunctionalized. What's the best way to functionalize an alkane? Radical bromination. So we'll do Br2, we'll do UV. All right. Now we're getting somewhere. The problem is, how do we get from a haloalkane to a ketone? We might have to do a few intermediate steps though. So let's even put in our ketone. And then we'll kind of fill in these gaps as we go along. What Grignard reagent should we use too? Yeah, if this is the case, we know immediately in this step we need methyl magnesium bromide. Oop. Followed by water. Okay, if we do that, then our Grignard will look like this. Okay, so we're getting somewhere. We've got our beginning, we've got our end, we've got our middle. Now we've got to connect the dots a little bit. How can we go from a tertiary alcohol to an alkene? Yeah, concentrated acid and heat. So I'll just write cont H plus and heat. By doing that, we'll do an elimination. Is this E1 or E2? E1. I saw a lot of people doing tosylation or conversion to a bromide and then do an E2. That works as well, but if you're a chemist, you probably don't want to make your job any harder than it needs to be. It's a lot easier to do this reaction in one step than it is to break it down into three. All right, so now we've gone from the middle all the way to the end, but we still have to figure out how to get from our haloalkane to our ketone. Does anybody have an idea? Oh, so you can make a ketone with PCC? Okay, I think that's a great idea. So we'll use PCC. What would our starting material be? Yeah, exactly. So we can oxidize a secondary alcohol to a ketone using PCC. What was the other reagent that also works? Yeah, sodium dichromate and sulfuric acid, or just chromic acid, or one of 9 other reagents you might see in your book. They're all ways of making chromic acid, though. Either method works. PCC is more gentle than chromic acid, so oftentimes that's the preferred route. All right. Can we immediately substitute that bromine for an alcohol? Why can't I just throw in sodium hydroxide and do SN2? What's a problem we might run into? Does anybody have an idea? Oh man, last term feels like forever ago, doesn't it? Secondary carbons, if you use a strong nucleophile that's also a strong base, will favor E2 as your major product, and SN2 will be your minor product. So make sure you are comfortable remembering the SN1, SN2, E1, E2 pathways. However, one way around this is to do elimination. So we could immediately just drive E2 by using a non-nucleophilic base like sodium hydride. And then, how could we get an alcohol installed to that alkene? Yeah, dilute acid. So we'll write H plus and H2O. All right, so this one was a little tricky. It involved a fair number of reactions from this term and last term. But one thing I'll really challenge you guys to do is to go back and study not only materials from chapter 9 and 10, but even material from chapters 7 and 8, especially if you're a little bit rusty on substitution and elimination reactions. Does that make sense? Everybody's giving me a lot of blank stares. Was this too hard? No? Yes? All right. If you guys do get stuck, remember whiteboards are your friends. Working in groups is really valuable. I'm going to create a set of synthesis flashcards for us to use too as another study aid, and I'll hopefully have that ready by next week. All right, before we finish up alcohols, remember this flow chart is really useful. I would recommend going through and basically whiting everything out of that flow chart, all of the reagents, and see if you can fill them in by memory. If you can't fill them in by memory, make sure that you do review all of those reactions. So for this specific flowchart, I went through and I whited them out for you. You're welcome to print them off of the course notebook just as a good study aid. All right, let's go on to ethers, thiols, and sulfides. Chapter 14. In order to maximize our class time, I'm going to ask that you review nomenclature at home. It's sections 14.2 in your book. And then I'll also post an online video onto the class website as well, so if you do want to watch a short video, it can help you name ethers. Yes, it should be recording. Let me double check. Is it? Yes, it is recording. Thank you. No, chapter 14 will not be on the quiz. All right, so let's just do a basic intro to ethers. All right, the functional group for an ether is always going to be an oxygen in between two alkyl groups. Remember that R group that I'm showing just means it's some sort of hydrocarbon, usually an alkane coming off of there. Oftentimes those R groups are identical, so you could have something like diethyl ether where you've got two ethyl groups that are covalently bonded to that carbon. And one really nice thing with ethers is that they can be H-bond acceptors. What does it mean when I say an H-bond acceptor? Nobody? Yeah. Yeah. Yeah, so if we have another molecule that has the potential to hydrogen bond, and I'll just call this R, this can be a hydrogen bond acceptor because of this lone pair, right? This lone pair can actually coordinate with a hydrogen on another molecule, and you see ethers involved in a lot of organometallic reactions, and they specifically coordinate to metals and groups that hydrogen bond. Another nice thing with ethers is that they're weak Lewis bases. What does it mean if something's a Lewis base? You guys are tired today. What does a Lewis base do? It doesn't donate protons, it doesn't accept protons. In this case, it stabilizes the Lewis acid by the donation of electrons. Specifically, that green lone pair I circled, that can coordinate to a Lewis acid like a metal. Another nice thing with ethers is that they're fairly inert, meaning that they're non-reactive, which makes them great reaction solvents. You don't want your solvent to usually participate in reactions. And they're common functional groups in drugs. And drugs and solvents. So if you go through and you look at a list of the best-selling drugs in the United States, quite a few of them have ether functional groups in them. All right, so let's go back a little bit and talk about why ethers are so great at being Lewis acids. We talked a little bit about this last chapter, chapter 9, with borane, with our anti-Markovnikov hydration. In this case, the borane was always complex with what? THF. So THF is a special type of ether, and the THF is short for tetrahydrofuran. And so borane, if we look at it, is trigonal planar. However, the borane is stabilized by the lone pair on the THF. So you see THF is a pretty common reaction solvent because it's polar and it can coordinate well with a lot of different metals. Another situation where you see ether involved in is from last chapter, where we've got a Grignard reagent. And I told you guys really briefly that oftentimes you run these reactions in ether solvent. Specifically, diethyl ether is pretty common. And the reason for this is that this magnesium has a really, really strong delta positive charge. In fact, it's almost cationic. And this carbon's really, really electronegative. So again, this lone pair from the ether can help stabilize the magnesium in a Grignard reaction and allow this reaction to occur. In fact, you really don't see Grignard reactions take place outside of ether solvents. So they're really important for that. So let's make a list of some common solvents really quick. All right, the first one looks like a bat. And we've got two ethyl groups coming off of it. What do you think this is probably called? Yeah, diethyl ether. Has anybody seen Fear and Loathing in Las Vegas? Okay, never mind. There's a reference to ether in there. This one we mentioned before is called what? THF, or tetrahydrofuran. The last one that you occasionally see is called 1,4-dioxane. These are the three most common ether solvents that you typically run into in an organic lab. All right, and then I've got this family picture down here. I found this on the Master Organic Chemistry website.
Just scroll out a little bit.
Yeah. And if you notice, this family looks pretty calm, mellow, inert, except for the one kid in the corner. He looks a little out of place. There's another class of ethers that isn't inert, and we've already seen it. Does anybody know what ether is really reactive? Yep.
This against peroxides?
So peroxides aren't really classified as ethers because they've got an oxygen-oxygen bond. But I'll give you a hint. Do you guys remember when we used MCPBA? We formed an ether, and what was that ether called? Epoxides. So epoxides are the black sheep of the ether family. And epoxides, we've already seen these before. And to form an epoxide, we need an alkene. And I'm going to label this with an R group. And let's even label these R groups as R prime, double prime, and R triple prime. And we said if we react this with MCPBA, we'll always get this three-membered ring called an epoxide. So we're already familiar with this class of ether. And we end up with a mixture of enantiomers for this specific situation. Oftentimes, if you go through older textbooks, they don't refer to these as epoxides. These can also be known as oxiranes. And they are the most reactive ethers that we have access to. Why are they so reactive? Why are they unstable or reactive? Yeah, the bond angle strength. If we look at this, those angles in that three-membered ring are about 60 degrees. What's the preferred angle for an sp3 hybridized carbon? Yeah, about 107, 109.5. So in this case, we're forcing a really unnatural bond angle, and because of that, these epoxides or oxiranes are quite reactive, and they're also synthetically useful because of that. We are going to skip epoxides for right now, but we're going to study this next week. Oop. So we'll put that on the back burner for right now. All right, there's a couple other ethers I do want to mention. The first one is kind of a cousin of epoxides. It's got a four-membered ring. The other one looks like THF, where we've got a five-membered ring. And there are quite a few more. You can look them up in your book if you want, but they all have more and more elaborate names. The four-membered rings are called oxetanes. Five-membered ring is called oxolane. And you can keep on going into bigger and bigger rings. I'm not going to expect you guys to know these. Oftentimes you may see them in a textbook. However, they're not commonly used in our textbook, at least. Yep.
Is there a difference between oxalane and THF?
So oxalane is the functional group. THF is the specific molecule. So if you do see a 5-membered cyclic ether, we would call that an oxalane. If you see THF, THF is a oxalane too. Yeah. All right. So let's continue on. And there's one topic in your book that holds a special place in my heart, so I'm going to cover it. These are called crown ethers. And my PhD at the University of Oregon was on host-guest chemistry, and crown ethers were the original host-guest systems. And they're really elaborate ethers. You can see why they call them a crown, right? It's a big ring with oxygens in between. This ether is called 12 crown 4. You can synthetically make this. You can even just buy it from a chemical company now. And they tried making different size crown ethers. So in this case, this one has 4 oxygens in it. The next one we have looks pretty similar. However, we've got 5 oxygens in it. So I'll draw in our oxygens first. And in this case, this is called 15 crown 5. And then the next one that they made was one with 6 oxygens in it. And I can't remember what year the Nobel Prize was awarded. Oops, that's too many. Sorry. I can't remember what year the Nobel Prize was awarded for this chemistry. But it was a really big point in chemistry where we finally had the capacity to synthetically make molecules that bound other molecules. All right, so this is called 18 crown 6. So in this case, they almost act like little baskets for other molecules, and other molecules just fit straight inside. So 12 crown 4 is kind of unique because it will securely hold a lithium cation. Why will it hold the lithium? Why would lithium prefer to be snuggled into that little pocket there? Yep. Yeah, the lone pairs on the oxygen. So we just said that ethers are really good Lewis bases. They like to coordinate to partial positive or full positive centers. Lithium just happens to be the right size where it holds really tightly inside 12 crown 4. If we go on to 15 crown 5, what do you think might fit in 15 crown 5? Sodium. So sodium fits really nicely in there. Lithium's too small in this case. It doesn't bind as tightly in 15 crown 5 as it does in 12 crown 4. And then what about 18 crown 6? Potassium, because we're getting into bigger and bigger cations, and so in this case we can bind them very, very tightly. You may be wondering, why do you care about this? It looks kind of silly. Who wants to bind lithium, sodium, or potassium? It really comes down to the way that nature works. And so this is a compound that I pulled off of Wikipedia. This is called vanillamycin. And in this case, it binds potassium 1 million times more strongly than sodium. And in this case, the sodium fits right in this pocket. So it's another example of host-guest chemistry, this time not with the oxygens on ethers, but the oxygens on amides and esters. But either way, it shows a similar host-guest chemistry relationship to the crown ethers. And in this case, vanillamycin is one of the most potent antibiotics available to us. Another cool reason that these crown ethers are important is it allows us to do chemistry that used to be impossible. So let's say I try to do this substitution reaction, and I've got potassium and I've got fluoride, and I'm running this in benzene as my solvent. You get no reaction. Why do we get no reaction?
Benzene's too stable.
So benzene is just a solvent, but did we ever see substitution reactions with fluoride? No. When we covered chapter 7, we really never saw substitution reactions with fluoride. The reason for that is that the association or that ionic attraction between potassium and fluorine is so strong that that fluoride ion will never get a chance to approach an electrophile. So what they do is they try to break up that ion pair. And in this case, what crown ether would we like to use if we want to break up this ion pair? Yeah, 18 crown 6. And by doing this, the crown ether wraps up that potassium cation, exposing that fluoride, which makes it really reactive, and you're actually able to get new carbon-fluorine bonds to occur. So host-gas chemistry is, in my opinion, pretty cool stuff. We're mimicking biology in a lot of ways, and we're using it as a new synthetic tool. And if you guys do ever want to talk about crown ethers and host-gas chemistry, I'll talk your ear off. So you're welcome to come to my office and talk about that if you want. All right, let's go on to preparation of ethers. And I'm going to show you guys the industrial method. The industrial method for prepping ethers works really well for simple ethers.
Why we have to have a lab preparation and industrial preparation?
Your book presents both, and I think the ACS exam has both as well, so I want to show you guys both.
I mean, what's the difference? Why we can't just using one way to do a lab? We both feel like a lab.
I'll show you guys why. So in this case, this works well for simple symmetric ethers. So the reaction that's pretty common is you could take something like ethanol. You can treat it with a super strong acid, something like HI. And this alcohol will first get protonated. And then if you've got another equivalent of ethanol around, the second equivalent of ethanol can do an SN2 reaction, kick off our water. And then the water that was formed can grab this proton and do our final deprotonation step. And we regenerate our acid catalyst in this case. So this method works pretty well for making simple ethers. Why might this reaction not work well for other molecules that maybe have functional groups like aldehydes, ketones, alkenes, things like that? Yeah, oftentimes we've got acid-sensitive functional groups, like an alkene, for example. If we reacted a molecule with an alkene and an alcohol, this acid could add across that double bond in the alkene and functionalize it in an unintended way. So in this case, this really only works well for simple symmetric ethers. It's reliable, it's high yielding, but it's not common for more complicated ethers. So let's take a look at the method that's used for more complicated ethers. And this is called the Williamson ether synthesis. This is a reaction you guys know without knowing it yet. Let's say we've got this alcohol, and I treat it with sodium hydride. What will happen? So do you think we'll get an E2? Do we have a good leaving group? No. Hydroxide's a pretty crummy leaving group. Sodium hydride's a really good base. What might happen? Yeah, we'll just deprotonate it. We'll form our alkoxide. So we'll get O minus, Na plus. That's our alkoxide intermediate. And then hypothetically, let's say I want to react this and I want to make, whoops. This guy. What reagent could I react my alkoxide with to form this final ether product? Looks like we did some sort of alkylation. What do you guys think? I heard somebody say it in the back. They said bromopropane, I think.
Yeah.
Okay, so let's say we use bromopropane. What happens if we react this alkoxide with bromopropane? What sort of reaction would this be? Yeah, it'd just be a simple SN2 reaction. This guy got a reaction named after him by using simple SN2 chemistry. Pretty lucky in my opinion. It's just a simple SN2 alkylation with an alkoxide. It's really common, it's very reliable, it can be used to make all sorts of different ethers, and in fact you guys did this on one of your synthesis worksheets already. The important thing to remember with the Williamson ether synthesis is that you must form an alkoxide. You can't just throw an alcohol in there. And by doing this, you create an oxygen that's a good nucleophile. And this good nucleophile can attack with any sort of primary or secondary electrophile. Or sorry, methyl or primary electrophile. You normally don't see it with secondary carbons. Why don't you normally see it with secondary carbons? Yeah, exactly. It prefers elimination with secondary carbons. Therefore, we tend to use primary or methyl electrophiles when we're doing a Williamson ether synthesis to avoid that E2 side product. You might occasionally see it with secondary, but there's a good chance you're going to get a major E2 component out of the reaction. All right. We also know another way of making ethers. So let's review one of our old methods. This is alkoxymercuration. Demercuration. And when did we cover alkoxymercuration reactions? Chapter 9. So let's briefly review Chapter 9 materials. In Chapter 9 we said if we've got an alkene, we can react it with a mercury compound. What was the mercury compound we used? Yeah, mercuric acetate. So HgOAc2. And then we used water, and I'm going to abbreviate that. And then in the second step, what did we use to reduce off the mercury? Yeah, NaBH4. Same reagent we use for reducing ketones and aldehydes, but it's also a good reducing agent to remove that mercury from Chapter 9. When we do this, we get an alcohol installed, and we typically end up with an enantiomer out as well. If you remember, this always goes through Markovnikov addition. And in this case, why would we ever use the mercury method as opposed to acid catalyzed hydration? Yeah, it prevents rearrangement. And let me go back and actually color code this. I'm going to change this alcohol to blue. What do you think we could maybe do if we wanted to make an ether instead of an alcohol using an alkene?
Alcohol instead of water.
Yeah, it's as simple as that. If you want to make an ether, don't use water. Use another alcohol, something without that red hydrogen coming off of it. So for ethers, it's super similar. First step, we still use mercuric acetate. Step 2, we use sodium borohydride. And then when we do this, we now get an ether installed. And in order for this to happen, we have to use an alcohol, not water. Just like with the other one, this avoids rearrangements. You get a mixture of enantiomers out. All you have to do differently is use an alcohol. Does that make sense? Okay. I know this seems like a lot of material, but a lot of it's review, so I'm trying to go through it relatively quickly here. Do you guys want to review the mechanism for oxymercuration?
We can just skip to like
The mercurinium ion? All right. So let's
do we need to know
let's see the mechanism review. I have a feeling some people might have forgotten it. Remember, the first step always involves one of these acetate groups falling off. And when we do this, we now have a positively charged mercury. And if we treat this with our alkene in the above example, what happens? We've got a mercury with a positive charge. That's definitely going to be an electrophile. What will be the nucleophile? Double bond. So our double bond will attack our mercury. And when it does this, it will form our mercurinium ion. So we'll get Hg plus, and I'll just call this OAC. And now when we've got our alcohol around, which side of the mercurinium ion will the alcohol add to? Or does it matter? It doesn't matter in this case. We know normally it goes after the more substituted side, but in this case there's not really a more substituted side. So we'll just pick one. And we've got HgOAC. We've got our alcohol added in. This is anti-addition, so it's important to remember our regiochemistry still. And then what's our last step? Deprotonation, so we'll do minus H plus. I guess it's not quite our last step.
Can you do water?
What's that?
Can you do water?
For the deprotonation? Really, any gentle base will work in this step. Normally you do a reaction workup that will quench the reaction and deprotonate it. So now we've got our anti-product, HgOAC. And how do we remove that mercury? Yep, NaBH4. We've got to reduce off the mercury, and now when we do that, we end up with our new ether. And I believe that this reaction is not regioselective, or sorry, stereoselective. So this methyl group could be a dash or a wedge, but in this case it doesn't really matter, right? And why does it not matter? Yeah, it's not a stereocenter. So if we want, we can just go through and we can draw it like that. And I'm just going to erase this for clarity. All right, so make sure you guys are comfortable doing the oxymercuration reaction. I know most of it's review from chapter 9.
So we don't need to know how the NADH4 gets rid of the...
No. Yeah, you should know the mechanism with the mercurinium ion, though. Is there another question in the back? No. Ramon's just stretching. All right, so now let's do a brief introduction to reactions of ethers. Ethers, in their general form, meaning the non-epoxide ethers, tend to be quite inert, except under super duper acidic conditions. So let's try to rationalize what happens if we treat this with a super strong acid, like hydroiodic acid. What do you think the first step will be? Yeah, exactly. We could actually protonate this. However, in order to protonate the oxygen on an ether, we must use hydroiodic acid or hydrobromic acid. Hydrochloric acid is not strong enough in this case.
Is it double bond?
No, I'm just saying X equals bromine or iodine.
Oh.
Yeah. All right, so we'll protonate this oxygen on our ether. All right, when we did this, we also kicked off an equivalent of X minus, meaning we've got bromide or iodide around in solution. These are relatively weak nucleophiles. So what do you think could maybe happen? I'll give you a hint. We've got a super duper good leaving group on this side. Can attack the carbon and do an SN2 attack, right? So if we attack this carbon, we can kick this off because now we've got a great leaving group. So now we've got a halogen bonded to one of these carbons. Okay? And if we have more acid around, what do you think could happen next? Yeah, it can happen again. Just like we saw with our alcohol chapter, with primary alcohols, we can protonate the alcohol. That gives us an equivalent of X minus floating around in solution, and this can do a second SN2 reaction. And now we've got H2O. I'm just going to redraw our first equivalent. So you can use acid to cleave apart ethers. Whoops. Sorry, this should be an X here. You can use a super strong acid to cleave apart ethers outside of using hydrobromic acid, hydroiodic acid, or some other exotic acid. You typically don't see ethers doing much. That's why they're really nice solvents. One other thing that they mention in the book is that ethers undergo auto-oxidation, which was presented in the radical chapter. That's why ethers, oftentimes as solvents, have a use-by date on them, is they'll react with molecular oxygen, form explosive hydroperoxides, and they have to be discarded before it becomes a fire hazard. We're not going to cover that in this class because it's not synthetically useful. All right, I think that's where we're going to end it today. Be prepared for the quiz tomorrow. When we come back, we're going to move on to epoxides.